Just going to um, this will be then in control theory day one, and the book is feedback control. Control theory, feedback control. This mouse is pretty weird. Right? All right, let's just begin. We're going to do 2 hour 30 minutes. Uh, 120, 160. I mean, there will be timers, so don't worry about it. The timer will be here, and then that you can see that, right? And then we're also going to add this thunderstorm noise, or maybe like some calm noise, right? And Rocket, okay, so let's look at an example here. So Rocket adjusts mid-flight, or I'm going to zoom that in. So closed loops, the differences between closed loop and open loop. So step one, differences between closed loop and open loop. So closed loop, you have an out, goes back, and then it affects the system. So in a closed loop, it goes back. So I'm sorry, in a oh come on. In a closed loop, you have an output. It'll go back. It'll affect the system. So output goes back, affect the system. So once again, you have a you have an output, goes back, affects the system. I'm not going to read about open loop. I'm not going to even read about open loop because there's no point. Why feedback exists? Feedback is used to keep the thing stable, reduce error, handle disturbances like wind, noise, uncertainty. Step two, why feedback exists. Keep things stable. Actually, you know what? Where's the stopwatch there? So why feedback exists? To keep the feedback is used. Feedback used for keep things stable. Um, to keep things stable. Uh, reduce error and handle disturbances like wind or noise uncertainty. Okay. So what was the core point here? So we did it. We need so this is like a feedback. You measure, you compare, you correct, you repeat. Now, um, I have this. Explain the same thing using this as an example slowly. So what would my system do? So we have a rocket flying, and we know also know for a fact that the reality is not your model. So the reality will not be the model that you did or the maths you did. So mathematically, the real dynamics is not the same as the model dynamics. So one thing to configure is that. So one thing to configure. So this is 120. One thing to always configure is that the rocket that you're trying to fly, the reality or the maths that you have done, the dynamics, the real dynamics is not the same as the model dynamics. I'm going to put on a lamp light. So the real dynamics is not the same as the model dynamics, meaning whatever the maths, the model maths you did, so whatever the model, you know what? Fuck it, I don't give a shit. So whatever the model maths you did, they will not be the same as the real dynamics. So real dynamics will not be the same as the model dynamics. because you're going to have wind, you're going to have thrust variation, you're going to have air density uncertainty. So what happens without the feedback? So in an open loop, so you're going to have like some input, you're going to have a rocket. So what happens is, so in an open loop, in an open loop, you're going to have u of t, you're going to have, the rocket that's moving or doing the process. So you're going to have rocket and then it's going to have an output, right? But it's not going to go back again. It's not going to fix that. So in an open loop, it is not going to fix that as in it's not going to go back again and then improvise the model, go back to the rocket, I'll give the output, then go back in. It's not going to do that. And when you have that, like in an open loop, what happens is when you have x actual minus the x model, you're going to have a very large error. The reason for this large error, so 327, the reason for large error is that the actual value outputs one thing. So actual value outputs one thing, but it doesn't improvise it, right? But it doesn't have the program or the code to be like, okay, this is what you did. This is the mistake that you did. You have to go back again and check. But it doesn't have that feedback box, that feedback box that will allow the model to be like, okay, you made an error, go back again and check. Feedback box that will allow the user to observe. So you made a mistake, look at your output, you made a mistake, go back and change it. You made a mistake, you have a large error, you have a large gap error, made a mistake. So you have a large gap error, you made a mistake, go back again and change it. Go back again and change it. Right? It doesn't have that. So obviously there is no correlation. So once it outputs, so once it outputs, finished. It outputs. That's it. Now, after when the feedback is added, so this is where the closed loop exists. So after feedback loop exists, which then moves on to the closed loop. So this will be a closed loop. So now you're going to have x of t rocket u of t, and then it goes back again, improvises the model, goes back again, improvises the model, and then so on and so forth. And at first, obviously, you're going to have a large error, right? Initially, you are going to have a large error. That's completely fine. But after doing the so we're going to have error is equal to x desired minus x actual. Initially, you're going to have a large error. That's completely fine. But you're going to go back again, right? The feedback function is going to go back again, improvise it, go back again, improvise it, go back again, improvise it. So then you're going to have u of t being the f of error. So this will be your first error. Then it will be a second error, third error, fourth error, fifth error. And then error after error after error, you're going to see, the model being improvised depending on how you code it. So this is step 1, 2. So this is step 1. This is step 2. This is step 3. This is step 4. You don't know the true state exactly. So you're going to say you will estimate that x hat of t is approximately equal to x of t. So this is your estimation. This is not your exact value, but this is just your estimated value. And so what is the adaptive model? So normal model, you're going to have f of x and u, but in reality you're going to have updated parameters. So x, u, and theta of t. Theta of t is a changing parameter. So model is no longer fixed, but it's learning during the during the flight, and at each time step it's going to make sure that it minimizes the error. So it's going to minimize the, so it's like saying, so I'm going to actually explain step 5, step 6, step 5 and step 6. So step 5 and step 6 I'm going to explain in one hand. So step 5 and step 6. So in general, a normal model would have x dot would be f of x in u. Now this is a dot notation. First order differential equation dot notation. Now this only shows input and output. However, it doesn't have the changing parameters. It doesn't implement those reality parameters. Now, core thing to observe, so core thing to configure is that although it has input and output, it doesn't have the changing parameters, right? Although it has input and output, it does not have the changing parameters, which means your technically your final output becomes your final output. So you really cannot change it. So it does not have the final output. Sorry, not final output, changed parameter. Changed parameter, meaning your final output is actually a large error value, right? The final output value is your large error value. Now, this is a normal model, right? Now, a parameterized model, so we'll call it a reality model. A reality model, you're going to have x dot is equal to f of x u theta of t. This theta of t is the changing parameters. Changing parameters. You're going to have mass, you're going to have drag, you're going to have force, whatever. So this is not a fixed model anymore. It's like a curving model. So it's going to change over time. So this model, okay, so it's going to take time. So what happens is this model is not fixed anymore. If I were to take an example of this guy here, if I were to take an example of this here, best example for this would be, so if I say example for this, so if I launch a rocket, right, I'm going to state this is where I'm going to go up, like that will be my, you know, the angle bank that I'm going to fly up, right? But that'll be fixed because I don't have this parameter is going to change or whatever. I don't have that. If I set a certain angle, if I set a certain angle, then that is my final angle. I can't change it. Then that ends up as my final angle, meaning I cannot, change in between. I cannot move the, the rocket so that it lands, so that it changes the bank so that it reaches the destination or whatever. I can't do that. Meaning, if the launch is 23 degrees, but that is considered for the beginning, 23 degrees stays throughout the journey because you don't have the change in parameter. But that is focused only for the beginning. that is focused only for the beginning, you only have 23 degrees, right? You only have 23 degrees, but you won't be able to change the angle bank. You won't be able to do that. But you won't be able to change the angle bank. You don't have a parameter that will allow you to change that. Why? You don't have an angle bank that will allow you to change the parameter. I mean, what have you got? You only have 23 degrees. That's it. Your input was what? Um, so your input was 23 degrees, but your output may change. Your output may differ, but because it is 23 degrees, your output remained 23 degrees throughout. So because you don't have an sorry, you don't have an angle bank, you don't have a parameter to change that angle bank. You don't have the parameter to change the angle bank. To change the angle bank. You don't have that. So it's going to go 23 degrees throughout, meaning it will be 23 degrees throughout. Now, when you add this x dot is equal to f of x u theta of t, now it's going to change. It's going to change. It's going to change. So now it's going to be like, okay, I have an input, I have an output. However, I also know that during that motion, it's going to change, right? So I have input, I have desired output, and I have I have a parameter option where I will allow the model that's inside the rocket to keep on changing. And I have the parameterized model that will allow the user, not the user, but allow the rocket to change the angle bank continuously. To change the angle bank in order to minimize the error. So technically, if I were to bring this equation again, optimization equation, an equation, and I'm going to have that theta of t specifically would be minimum for u, j of x and u. So x input remains as it is, but the minimum of u means, let's say, like theta of t is what? X desired minus x actual. And if the x actual is less, no, if the desired minus actual, if it's like extremely high, then obviously there's an error. And the actual value may end up being way smaller than the desired. So it's going to minimize the it's going to continue to minimize the error, not minimize the bank, minimize the error. So if you're told that your desired is 30 degrees, but then the actual ended up like 10 degrees or maybe 5 degrees, so it's going to increase the bank. This x desired minus x actual theta of t, you're going to make sure you minimize the error, not minimize the bank, but minimize the error. So if it's like, if x desired is 30 degrees, but x actual is like 5 degrees, then you're going to have to increase that, right? 5 degrees, 7.5, 10, 12.5, 15, so on and so forth, until it reaches almost 30 degrees. It's not going to be exactly 30 degrees, but almost it reaches 30 degrees. So you would have to increase the angle bank, to reduce the optimization error, right? So long story short, so long story short, long story short, you have measure, estimate, update, optimize. You have measure, estimate, update, optimize, and then apply it. So a measure is done by sensors. Obviously, you're going to have sensors. Then you're going to estimate. You're going to get some estimation value. You're going to update the model. So continuously, you're going to update to minimize the error. And then this is where the optimization comes in hand, because as you're going to continue updating the new value again and again, you're also optimizing it, right? So if you have like theta of t, and then that's it. So technically, in an open loop, you have measure, estimate, you don't have update, optimize, and then apply. So this optimize, also optimize doesn't exist. So this is a closed loop, closed feedback loop. In an open loop, like in how I understand, you're gonna have measure, you're gonna have, actually not measure, you don't need, I mean you measure, yeah, which is an input, rocket, output. So this output is u of t. Wait. This output is u of t in an open loop, meaning this is your final output slash answer. But this optimized, this u of t in a closed feedback loop is not output. It is not output, it is optimized, because you're going to continuously update it. So it's like you have this, this, then goes back again. But for here is this. End of discussion. But obviously you're gonna have many problems because the error for this will be way larger. So error will actually be very large. But here, error will be large initially, definitely. But then it's going to, optimize, and then error will be almost approximately equal to zero because it has optimized, right? Or what is control? Now go one step at a time. Like one step, let me understand, and the next step. Thank God I actually understood what's going on. And how many chapters do we have for chapter one? Let check. 1.0. Okay, 8 subchapters. Okay, let's you like what's going on here, dude? I found. Oh wow, what is going on here? Slowly, slowly, one step. Let me understand the next step. Control uses the information to force the system to behave the way you want. Meaning you're gonna have an input, so u of t, then it goes to a system, and then y of t. So you choose u of t such that the y of t is almost equivalent to the desired y of t. So you're gonna have, okay, I don't understand. So y of t is the actual trajectory. Y desired is the planned trajectory, and the u of t is like you steering. So you control the u of t such that you're gonna have your actual uh, trajectory is almost the same as the planned trajectory. How do we control that? Oh, he's going to go to the next one, right? Okay, he's going to explain the next one. So what is control? So this is step two. Step two, what is control? So control uses the information to force the system to behave the way you want. So it uses the information that is in front of you to force the system to behave the way you want. So it's like you're manipulating the system. So control is more of like you being the big guy and you're trying to control like the trajectory, like whatever you're trying to control. It's like you're trying to puppet that whatever you're trying to puppet, right? So forcefully controlling, it's not a bad thing, but forcefully controlling whatever you're controlling to make sure it behaves the way you want it to behave. So use information to force a system to behave To force the system to behave the way you want to behave. The way you want to behave. If you have u of t and system and y of t. So this u of t is, what you're trying to steer, right? So this is what you're trying to steer. I'm going to use this as an example of a car example. So you want to make sure that your main aim is make sure y of t is almost equivalent to y desired of t. So u of t will like you steering. So if like you are steering to make sure is you controlling. Oh, come on, you're so slow, man. So it's like you controlling. Yeah, it's pretty slow, not gonna lie. But what happens like u of t is like you controlling the steering wheel, right? So if you want to move right, you want to make sure that wherever the destination is, you control it right, and you want to control a little bit to the left. So it's the same thing for rocket. Says either going to go down, either going to go up, either going to go down, either going to go up, and this is where this continuously optimization happens. And I lost everything. I think I lost everything, right? Is you controlling whatever you're controlling, right? Controlling the vehicle. We'll just say you're controlling the vehicle. So if let's say, for example, y desired. So I'm going to use a real life example. So let's say, for example, um, Earth, Moon. You- Like to reach there, you want to make sure that you have to go like 23 degrees. Let's say, for example, you're going to start at 90 degrees, you're going to go up, you're going to turn to make sure you're going to go around rather than going up. So because if it continues to go up, then it's going to fall down, right? So you're going to make sure you go up, and then you have to change the angle, then change the angle again, and then you reach, right? Earth, Moon. So let's say this is the starting point. You're going to go like that, and then let's say that's a hit point. Pretty slow. So you're gonna say this, gonna go around. So I'm gonna use the Artemis example. It's gonna go like that, right? So here you see that there's a change in angle. So change angle one. Obviously, there will be many changes in angle, many, but I'm just giving an example. So change angle one, change angle two, and then change angle three, and so on and so forth, right? But see, it continues to change, which means you're continuously steering that. So this is where, oh, come on. So this is, so if I were to highlight this on dark green, so this section here, when you have x of t, x of t, rocket, u of t, this u of t, inside the u of t, you're going to have the system, you're controlling that system. So instead of u of t being the final output, u of t now becomes this steering wheel that you're trying to control to make sure it ends up y of t, where this y of t, you want to make sure that this y of t, this y of t is almost equivalent to y desired of t. So it's like you're now, instead of y u of t being the final output, so technically you're actually going to have u of t. I'm going to draw a bracket here. System y of t. This is what you're going to have. So it's like instead of u of t, I'm going to write a capital u of t. So this is what you're going to have. Instead of that being the final output, you're going to have that u of t as being the steering wheel that you're going to turn left or right to make sure that it reaches the desired angle or almost close to desired angle. Yes, understood. Let's go. How many steps are here for? How many steps are there in total for section 1.2? 5 core steps. Let's do step 3 now. Let's do step 3. Yes, let's do step 3. So E of t is y desired of t minus y of t. So this means that y desired is what you want, y of t is what you will actually have. Error is the difference between the target and the reality. So if the desired trajectory is the planned path and the actual trajectory is where the rocket really is, and if the rocket is off path, then error is not equal to 0. If the rocket is perfect, then obviously error is 0. Controller does not care about the absolute values, it cares about the E of t. So u of t is being the function of error value. It doesn't care about the absolute value. It doesn't care about, so you're not going to come up and be like, oh, f of 23 degrees. It's going to get the error. It's not going to get the actual value or your desired value. The function, the error function, will only tell you the error is too high, or you know, you're too high, you're too low. Like in the in Boeing, you're gonna have like pull up, whatever, right? So it's kind of like that. It's not going to give you the desired, like there is a complete different device for that, the actual angle or whatever. But here, it's not going to give you the actual angle. It's going to give you the error. So if it says, if you're like if you're like, if your angle bank is like too steep, then it's going to say you're too high. If it's like too low, then it's going to say too low. If you're off track, it's going to say off track. It's not going to give you the actual value. It's going to give you error value. Error value. So step 3, error core for control. So E of t is the y desired of t minus y of t. The y desired of t is what you want. Y desired of t is what you actually want. And y of t is your, what you actually see. So what you actually see. And the error is the difference between y desired of t minus the y desired of t minus y of t. So which means your u of t would simply be f of e of t. So when you're trying to control that steering or whatever, so you're going to only see too high or too low, almost there, perfect, right? So it's like saying when you try to do, when you try to control the steering wheel, so when you try to control a steering wheel, like, let's say, for example, if you have a device in front of you, let's say if you're trying to control the steering wheel and you see a device in front of you, and let's say, right? Let's say you see a device in front of you. So when you try to control the steering wheel and let's say you see a device in front of you, you're only going to see only going to see too high or too low or almost perfect like that. Oh, okay, I can't write anything if there's no battery. Just continue. Move to step 4. Move to step 4 and 5 in one go. Yeah, the system will not be an ideal model. The two things that mess everything up, so you have the disturbances like act on the system. So x dot would be f of x and u plus d of t. You're going to have the wind, you're going to have the drag variation, you're going to have the turbulence. The rocket will get pushed off trajectory, and the sensor will not give the exact value. So y measured would be y of t plus n of t. You're going to have sensor error, you're going to have electrical noise, you're going to have imperfect readings. Yeah, so it's that one there. So noise plus disturbance. So step 4, noise plus disturbance. The real system is not clean because obviously you're going to have system which is not an ideal model. You know what? I'm just going to stop for some time. Just stop for some time.